Today we'll be talking about how to find the inverse of a quadratic. So just remember what an inverse is. It's a relation that undoes the actions or operations of another relation. So how you find it algebraically and graphically are, algebraically, we know that if the function is called something other than y, you should probably call it y instead. Switch x and y and then isolate for y. Graphically, we know that they are just reflections across the line y equals x, which is, of course, just our diagonal parent function. So that is how you could graph an inverse given the graph of its parent function. Okay, so down here we have our graph. So first, we had to graph f of x, and you can see that our vertex is at -1, -2. So I started with that, and then I can also see there's no dilations here at all, no stretches or compressions. So it's just going to be the parent function shifted left and down. So that's where our purple f of x came from. Now we have to graph its inverse. So to help me, I graph the line y equals x because I know that it's just a reflection in that line. I changed colors here. So then I took each point on the original and I switched the coordinates. So here, this one was at -1, -2. And so I know its inverse will pass through the point -2, -1. And that's where that point came from right there. Similarly, I can see that the original passes through 0, -1. So I know its inverse will pass through -1, 0. And that's how it passes through this point. So I did that for all of them and got this blue function here. Sorry, not function, relation. And just visually, we can see that it is indeed a reflection across this line. And notice how I did not label this f inverse of x. The reason being that it's actually not a function. It fails the vertical line test. So I'm just going to call it inverse because I can't use function notation for something that is not a function. Domain and range. So you can either do this graphically or just understanding that the domain of a function is going to be the range of its inverse, and the range of a function will be the domain of its inverse. Of course, you still need to use x for domain and y for range. And is the inverse a function? Again, we already talked about that. It fails the vertical line test. So determine the equation of the inverse. Our first step was we let f of x be y. Then we switched x and y. And now we want to isolate for y. So don't forget your undoing of order of operations. We need to undo the subtraction first. Then we'll undo the square by square rooting. A really important thing not to forget here is the action of undoing a square makes there be a plus or minus. So don't forget the plus or minus. And now we subtract 1, and here's our equation. Again, I'm not calling it f inverse because we know as soon as we see a plus or minus, something is not a function. Now we want to be a little sneaky. We want to limit the domain of f so that its inverse is a function. So limiting the domain, that's sometimes necessary. In fact, that's what we do for trigonometric functions as well. So maybe we only want to consider part of this purple function here, because that way our inverse will be a function. So which part should we consider? It doesn't really matter, but typically mathematicians pick this right-hand side right here. Why we pick this part here is really because it's generally the most relevant in real world situations. And the inverse of that would correspond to this part right here. So that would be the positive square root. So again, we are going to only look at this highlighted part of f of x, which is from x above, greater than, or equal to -1. And its inverse, or its reflection across y equals x, is this blue highlighted part. So again, this blue part is now a function. So if we limit a function, we can make its inverse a function as well. So again, we only considered one side of the parabola. We considered that yellow side. And that's what made the inverse into a function. So this one right here. And we can see that the domain is related to its vertex. Okay. Now, again, we're trying to just determine the equation of the inverse. We let y equal our g of x. We switch x and y, isolate for y. Don't forget to do this in proper order. So do not divide by 2 first. You need to add 4 first. And again, we have a plus or minus here, which we don't want to forget because it has some implications. And again, we know that this is not a function as it is. So we're trying to think of how we can limit the domain of g of x so that its inverse is a function. You can kind of think of this in your head, but I know that the vertex is at -3, -4 from up here. So if this is at -3, -4, I probably want to take the right-hand side of that parabola, which would be everything greater than -3. So that's why I chose this domain so that I'm going to make the inverse a function. Okay, and scrolling down here, I'm graphing g and its inverse. So g, notice how it has its vertex at -3, -4, and it has a dilation by factor 2 vertically. So just keep that in mind here, that we can see that our step here is 2, and then it's 6 instead of 3. So just be careful with that vertical dilation. It's not necessary to draw the other side because we were only asked to draw the restricted function, but I'm just doing it as a dotted line just for like visual sake. So again, this purple function right here is our restricted g of x. We could have graphed this first if we wanted to help us find the domain, by the way. And then again, we're graphing y equals x and sketching its inverse here by switching these values. So again, instead of at -3, -4, it's at -4, -3. And visually, it is a reflection. And you can see that that is just the top half of the inverse. And it is a function, so I labeled it using function notation. So keep in mind here that if I do limit the domain like this, then I can say g inverse of x is going to be -3 plus root x plus 4 over 2. So again, I'm taking the positive square root, which is why it's the top part here and not the bottom part. Okay, thanks for watching.